Hello students, I am Subramaniam. Today we will be discussing mathematical induction. It is one of the most powerful tool in proving mathematical results involving n. It mainly consists of two steps. Firstly, we verify the result for n equal to 1, and then we assume the result for some value of n, say k, and then on the basis of this assumption we try to prove it for n is equal to k plus 1. For instance, if our question is to prove 1 plus 3 plus 5 and so on up to n terms equal to n square, that is, sum of the first n odd numbers is n square. This we have to prove. Our first step is to verify the result for n equal to 1. So, we have P 1 is equal to 1 equal to 1 square. It is obviously true. Thus, P 1 is true. Then we assume this for k, that is, we assume that P k be true. This means 1 plus 3 plus 5 and so on up to 2k minus 1 is equal to k square. Our next task is to verify it for k plus 1, and for this we add one more term both the sides, which gives us 1, 3, 5 and so on up to 2k plus 1, and here we have k square plus 2k plus 1, which equals k plus 1 square. Now, this shows that p k plus 1 is true. This is second step, and thus the result is proved for all values of n. Sometimes we cannot start the first step from n equal to 1. For instance, the problem to prove factorial n greater than 2 raised to power n. Here we observe that when n equal to 1, we have factorial 1 more than 2, which is not correct. Similarly, when you take n is equal to 2, we have factorial 2 more than 4, again not correct. N equal to 3, factorial 3 more than 8, again is not correct. However, from n 4 onwards it is correct. So, we first find P 4, that equals factorial 4 more than 2 raised to power 4. Of course, factorial 4 is 24 and 2 power 4 is 16. So, the result is correct. So, P 4 is verified. Thereafter, we go for P k. So, let P k be true. This means factorial k is more than 2 raised to power k. Now, from this step we have to prove that p k plus 1 is also true, and for that we have 1 factorial k times k plus 1 is more than 2 raised to power k times k plus 1. This side becomes factorial k plus 1. Here we can write this as 2 raised to power k times 2, because k plus 1 is more than 2. Thus, we have factorial k plus 1 is more than 2 raised to power k plus 1, which means p k plus 1 is true. Now, a question may arise: how will we decide where to start? The answer is simple. The question itself will guide where to start. In this question, factorial n more than 2 raised to power n was valid only when n was more than or equal to 4. We take the number which is the minimum which is correct for the required condition or the equation. Let us take one more problem. Suppose we have to show 1 cube plus 2 cube and so on up to n cube is equal to n times n plus 1 upon 2 whole square. When nothing is mentioned, it means we start from P1 only. So, we take P1, that is 1 cube equal to 1 times 1 plus 1 times this upon 2 whole square. Left side is 1, right side is again 1, so it is satisfied. So, P1 is true, the first step. Now, let Pk be true. This means 1 cube plus 2 cube and so on up to k cube is equal to k times k plus 1 by 2 whole square. As before, we add next term both sides, which makes 1 cube, 2 cube and so on up to k cube plus k plus 1 cube. This equals k times k plus 1 by 2 whole square plus k plus 1 cube. Right side equals k plus 1 by 2 whole square times k square plus 4 times k plus 1. This equals k plus 1 by 2 whole square times k plus 2 whole square, which means it is k plus 1 times k plus 1 plus 1 upon 2 whole square. This means Pk plus 1 is also true. Now, this completes second step, and hence Pn is true for all n belonging to natural numbers. We can have one more example, say 1 square plus 2 square up to n square. To prove it is to be n plus 1, 2n plus 1 over 6. Again, we first verify P1, that is equal to 1 square equal to 1 times 2 times 3 upon 6. This is true. Thus, P1 is true. Now, let Pk be true. This means 1 square plus 2 square and so on up to k square is equal to k times k plus 1 times k plus 2k plus 1 over 6. Again, to go for Pk plus 1, we add one more term. So, we get 1 square, 2 square and so on up to k square plus k plus 1 square. This makes k plus 1 times 2k plus 1 over 6 plus k plus 1 square. Now, right side equals again k plus 1 by 6 times k times 2k plus 1 plus 6k plus 1. This makes k plus 1 by 6 times 2k square plus 7k plus 6, which equals k plus 1 upon 6 over 2k plus 3 times k plus 2, which can be arranged as k plus 1, k plus 1 plus 1, 2k plus 1 plus 1. Thus, pk plus 1 is true. This completes the second step, and hence we can say 1 square plus 2 square and so on up to n square is equal to n times n plus 1 times 2n plus 1 by 6 for all n belonging to n. Often it happens that students have a doubt, why should we take P1 at all? Because they feel that P1 is playing no role in the whole proof. The fact is different. Let us see how it is happened. Suppose you have to prove 1 plus 2 plus 3 and so on up to n equal to n times n plus 1 by 2 plus 3. You assume it for k. So, let pk be true. This means 1 plus 2 plus 3 plus and so on up to k is equal to k times k plus 1 by 2 plus 3. Now, to come for pk plus 1, we add one more term. So, we get 1 plus 2 plus 3 and so on up to k and k plus 1. This side we get k times k plus 1 by 2 plus 3 plus k plus 1. This implies 1 plus 2 plus 3 and so on up to k plus 1 equals k plus 1 by 2 times k plus 2 plus 3, which equals to k plus 1 times k plus 1 plus 1 by 2 plus 3. This implies pk plus 1 is also true. Now, can we at this stage claim that Pn is true for all n belonging to n? No, we cannot, because if you check the result for any value of k, say n is equal to 3, what do we have? 1 plus 2 plus 3 equal to 6 in the left hand side, and in right hand side you have 3 times 4 upon 2 plus 3 equal to 9, while 6 is not equal to 9. So, we are arriving at a wrong result. Why it happened? What has gone wrong? If you care for P1, this becomes 1 equal to 1 times 2 upon 2 plus 3, which is not correct, because 1 cannot be equal to 4. So, this example clearly indicates that both the steps are essential in proving via mathematical induction. Today we have discussed mathematical induction. We have worked out 3 problems. Besides that, we also saw an example which clearly indicates why the 2 steps are essential. In our next episode, we will be taking some more problems of different type, including the one in geometry. Thank you very much.